sending English text. In the English text, the letter E occurs way more frequently than the letter Z, for example, in just average English text. So the idea is, why not use fewer bits to represent the letter E, which is more frequent, than the letter Z, which is less frequent? Is there a way to come up with a kind of representation where the number of bits used to represent each character will be balanced out at the end, by the time I'm done encoding the text, in such a way that I will end up using fewer bits than if I were to use simply ASCII or Unicode to represent my text? One such encoding is what's called Huffman encoding. So let's see how Huffman encoding works here. So let me see what I have here. Should we do the Mississippi River? It's kind of a lengthy example, but we'll do it. I think we'll be done in 10 minutes. Okay, so here's what's happening. If I used ASCII to represent Mississippi River, it would take me 136 bits to represent the entire message. Now let's come up with another scheme called Huffman encoding that will use fewer bits to represent the same message. So let's see. I'm going to look for a character that has the highest frequency of occurrence in my text. So in Mississippi River, which is my entire message, the letter I appears super frequently. And the letter V does not appear that frequently. So what I'm going to do is I'm going to end up using up fewer bits for the letter I and S, those letters that occur frequently, and those letters that don't, like V, will use up more bits. You start from the leaves. This stands for space. And I'm going to say that space occurs one time. This is going to be my node. Okay, so this is going to be my node. I'm going to have another node that consists of one character, that is E, occurs one times. That's another node in my tree. V occurs one time. That's another node. I have a feeling it won't fit here. Okay. Then I'm going to have another node that is R. And I'm going to write down notice that I'm writing down a dictionary, like you had in the homework assignment. You had a tree. The tree itself stored two pieces of data, key and value. So my key is R, and the value, the frequency with which this R occurs, is 2. Okay. Then I have my P. I'm looking at this table, basically. I've built first I look at the frequencies of the letters. P occurs 2 times, and so on. So S occurs 4 times, and then I occurs 5 times. And then, of course, I have my M here. Let me put that M on that side. Okay. And then I have my M here also. And this takes just one character. I'm going to do the following. I'm going to take up 2 entries that have the smallest values. So here, for example, in this example, I have a bunch of characters that occur one time. So for example, this space, for example, and M occur one time. I can go ahead and combine them into a single node. I can pick any of these 2 characters. So let's pick, for example, E and space. I could have picked space and M. It doesn't matter, but I'm picking E and space. And I'm writing, and I'm combining this into a single node. The single node I'm calling just simply E space is going to be the name of this node, E space. Then I'm going to combine M and V, for example. Hold on 1 second. Let me just move it so that my tree looks okay. Okay. My tree looks okay. So let me just draw it like that. Okay. Okay. So that the tree ends up. So inside the computer, this, the way you arrange these doesn't matter. These are just nodes. I'm just drawing them. Now you can combine another lowest 3. So this guy has value 2. Right now I'm going to place a 2 there when you combine E and space. So I place a 2 there. Now I'm going to combine these 2, V and M. So V and M node. And actually, let's write it down this way. E and V. And I'm going to have 2 here. V and M, I'm going to have 2. Again, now these guys are not my nodes anymore. my nodes are this, 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 this. And these are the nodes now that I will look at to determine which two of them have values that sum up, that are the smallest. And then I will combine the two nodes and sum up the values. So which two are the smallest? Okay.
P2 and R2?
Yeah, P2 and R2, for example. Or I could combine this with that. That will also be a combination. I could draw a node just like that. Or I could combine these two. So notice that I have some freedom in choosing which nodes if there are ties. So if you're given this question, you will be given this question normally, like this question, this exact question showed up a couple of semesters ago on the final exam. So that's why I'm going through this one. So you will be asked to resolve the ties alphabetically, whatever. You'll be told how to resolve the ties. But here, wait, let me just go with P and R. So I'm going to say that I'm combining P and R, and the value of this node is going to be 4. Okay? Now I have to combine the smallest ones. So which are the smallest ones? Again, so people realize what the steps are, right? So now what are the smallest nodes? This guy and this guy, for example. No, not for example. Actually, here I don't have a choice. These are the smallest ones. Okay, so which ones have I combined? V, M, and E. And sorry, it's the space. This should be a space. Why did I put a V? I don't know. And space. So this is going to be 4. Okay. Then, what am I doing next? Let me copy the whole thing because I'm running out of space onto the next page. Onto the next page here. Okay. So what's my next step? What should I do next? Combine. Yeah, sorry, one more time.
You have to combine any of the nodes that have a value of 4. So you could do S, PR, or VME space.
Yes, I could combine these two. I could combine these two, for example, right? So I have these two choices. So let's combine, I don't know, PR and VME nodes. I don't know, let's do it that way. Okay, this kind of one-sided tree. So now my node here is going to be 8. And this 8 has P, R, V, M, E, and space. So that's the name of the node. And it has the value 8. Now, what is the smallest now?
Just S.
Sorry, one more time.
Just S4.
Just S4 is the smallest one, but I have to combine it with something so I get the smallest one. So what are the two nodes that I can combine so that I get the smallest, the next smallest value possible?
I5 and S4.
Yeah, 5 and S4. So I'm going to call it IS, and it's going to have the value 9, right? So that has the value 9, and now I'm done with. Okay, so now what's the next step? I only have 2 nodes left, so I don't even have to think at this stage. I'm going to combine these two, and I end up with IS, P, V, M, E, and space, and I have 17 is the value. Now, of course, this 17 here better be the sum of these numbers here. If you add up these numbers, 1, 5, 4, 2, 2, 1, 1, 1, they should add up to 17 because 17 is the total number of characters. Okay, so now this may not be clear still. I mean, so I built a tree, so what? Okay, now I have to actually encode the message. So this Mississippi River is going to be sent using an encoding. And here's the way the encoding is done. So you start at the root. Every time you come to the left, to that branch, you attach a 0. Every time you come down a branch that is a right branch, you attach a 1 to it. Come down to this branch, it's going to be a 0. This branch 1. This branch 1, 0, 0, 1, 0, 1, 0, 1. So you label all the branches that you have. And now encoding for any letter is the sequence of bits that you see when you follow the path from the root down to that leaf node. So that's why all the characters were leaves. There is a single unique path from the root in any tree, from the root down to that node. So for example, what's the encoding of V? So what's the path? You go down 1, 0, 1, 1, 0, 0. The only way to reach V is by 1, 1, 0, 0. Okay, what's the only way to reach S? What's the encoding of S?
Just 1, 0.
1.
0, 0, 1, right? 0, 1. So notice that to encode S, it takes me just 2 characters. S was very frequent. To encode I, how many characters does it take me? Well, I count down 0, 0 is the encoding of I. Okay, those characters that were most frequent, like S, it appeared 4 times in the original text. It only takes 2 characters to encode it. That character which was so frequent, it's as frequent as I, which is like 5. 5 times it occurred in the text. It only takes 2. A character like space, which occurred 1 time, encoding for space, is going to be 1, 1, 1, 1 in this encoding. 1, 1, 1, 1 is the way you encoded space. So you get the idea, right? So this is the encoding. Now let's see how many bits does it take to represent this Mississippi River. Okay, let me just write it. Okay, let's just send the Mississippi, River. So what's the encoding of M? 1, 1, 0, 1. So I write down 1, 1, 0, 1 here. What's the encoding of I? 0, 0. What's the encoding of S? 0, 1, 0, 1, right? 0, 0, 0, 1, 0, 1, 0, 0. What is the encoding of P? P is here, occurs twice. What's its representation? 1, 0, 0. You write this down as 1, 0, 0. Okay, 1, 0, 0, 0, 0. Space, 1, 1, 1, 1. That's the space. What's the representation of R? Okay, so you get the idea, but let's write it down. So then we'll count the number of bits. Where's my R? 1, 0, 1. So I write it down as 1, 0, 1. 0, 0. What's the representation of V? 1, 1, 0, 0. I have it here. 1, 1, 0, 0. What's the representation of E? So you get the idea, right? So help me out. What's the representation of E? Make sure that people are not sleeping, because everyone understood, and now people are taking a nap, right? 1, 1, 1, 0, right? 1, 1, 1, 0. Anyway, how many bits did it take me to represent this? It's clearly not 136 bits. It's clearly fewer. Okay, so it's 4 plus 2 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 plus 3 plus 3 plus 2 plus 4, 3, 2, 4, 4, 3. So you can add these up. I don't know how much that is, but it's clearly not 136, right? Actually, let's add this up. How many 2's I have? 1, 2, 3, 4, 5, 6, 7. That's 14. So up to here, I have 18. Then I have 6, 6. I have another 6. I have and 10. So that seems like 28 plus 18. That seems like 46 to me, unless I made a mistake. So it took me like 46 bits to represent the whole thing, right? It's not 136 bits. There's that many bits to send the text, right? Does that make sense how Huffman codes are built? They're used to compress information. You can use this in images as well. Okay, some variation of it. What else do we need to do? How about building a heap? Build a heap. So build a max heap from the following. let's say 8 elements. And I'm going to have these elements be, let me pick what I have. 5, let me just use example that we have. 5, it says 21, 68, 1, 80, 91, 97. Okay, do people see, is this neat enough for people to tell what's happening? Let me just redraw this. Let me just so 5, 21, 68, 1, is that 1? 42, 80. So how would you build a heap? Okay, so suppose you have this array to process. Okay, this is what you need to process. And you need to build a max heap out of these. Some priority queue application. These are your elements. So help me out. What would you do? Okay, so help me out. I'm going to draw a binary tree that will help me represent drawing my complete binary tree, okay, with 8 nodes. Okay, this is not a heap yet, not a heap yet. Okay, and turn it into a heap. Right? Is it clear what we're doing? Okay, let's start drawing this. What's going to be my root?
97.
Okay, all right. So we want to build the heap out of it. So you're asked to recall what exactly is it that this build heap operation did. Okay, the root is the first element at position 1 to begin with. This is not going to be a heap yet. We're building a complete binary tree that is not a heap yet. So 5 goes into this root position. What are 5's children? I know that I have, my tree will look like this because I'm building a complete tree, and because I have, well, how many elements do I have? Right? Okay, is there anyone here? Or am I just speaking?
Yeah, I'm here.
Okay, good. So those of us who are here, can you help me out? How many elements do we have? Why did I draw this tree and not anything else? Because I have, yeah.
There's 8 elements in the array, and that's the complete binary tree for that.
Yes. Okay, so I place the first element in the root. Where are its children? Where do I place 21 and 68 in this tree?
To the
here, right? What do I put in these 2 nodes?
1 and 42.
A 1 and 42? Exactly. Why is that?
You don't have to maintain heap order yet. You're just sequentially adding them to the tree, or the array, I guess, in reality.
Yes. 21's children, because 21 is at position 2, 1 is at position 2 times 2, and 42 is at position 2 times 2 plus 1. Right? Those are the children of 21. What are 68's children? Here's 68 is at position 3. 68's children are going to be at positions twice 3 and twice 3 plus 1. Okay, so 80 and 91 will go as children of 68. Okay, so this is 80, this is 91. Where's 97? Whose child is 97? It's 1's child. Okay, so where's 1? Here, at position 4. Where's 97? At position 4 times 2. Okay, again, remember, we start counting at 1. Okay, so 1 is position 1, 4 times 2, that's it. So 97 goes there. Now, what's the next step? Okay, so that's the first step. I read the data into my program. Okay, this is the array in which that data that came in is placed. We visualize this as this tree, and now we're going to turn this into a max heap. What do I do? Okay, step 1.
You start at the leaves.
Yes.
So you start at 97, you swim it up.
Turn this into a heap. Okay. So yeah, let me just do what you've just suggested. So start at where? What should I say?
Is it n divided by 2 is forward, so where the leaves start?
Yep. Length of let's call it array A. Length of A. Okay, so in Java this would be A length, okay, without braces, but I'm being informal here. This is pseudocode, it's not Java. Divided by 2, so that's where I start. And that's going to be at position 4. 4. So where's my position 4? 1, 2, 3, 4. So I start here, okay? And then what do I do? So 1 is at index 4. Does it violate the heap? 1 is at index 4. So let's say 1 is at index 4. Okay, so I is 4, index 4. 1 is at index 4. What does it do? It violates the heap property, right? So what do I do? Okay, so because, just to be clear, some people may not remember, 1 is smaller than 97, and we're building a max heap. So what do?
You exchange the values in the 2 nodes and then divide I by 2 again.
Okay, so what's the next step of the algorithm? Let me copy this. So how did my array change in memory? So, okay, can you repeat what you just said? I'm sorry, I may have missed it.
Because heap properties violated, you exchange 97
Yes.
and 1 their places, and then you divide I by 2.
Yes. Becomes I exchange 97. I exchange 97 with 1. So 97 goes here, and 1 goes here. And therefore, my tree, you first exchange, because you're restoring the heap property. So now heap becomes 97 here, 97, and 1 here. Okay? Okay? So that's clear, right? So what just happened? Okay? Just to be clear, my indices are 1, 2, 3, 4, 5, 6, 7, 8. I've exchanged whatever was at position 8 with whatever is at position 4. Those are shown here in black. Okay? Now, as you've suggested, step 2. Step 2. Decrement I. So what was I? I was 4. So now I is 3. So I am right here. Okay, so this piece Does it violate the heap property?
Yeah.
Okay, not a heap. So restore the heap property. How do I restore it?
This is where you want to compare the children's values, right?
Yes, exactly. So 68 is smaller than 80, and both 80 and 91. So what do I do?
So you would like compare 80 and 91. You'd say 91 is the greater one. And then since 68 is less than 91, you swap those. So 91 will be greater than 80 and 68.
Okay. So exchange. So we call these sink operations, right? Sink and swim operations. So you sink 68, exchange 68 with 91. Why did I pick the larger of the two? Can I ask you this? So you gave a correct answer. Why didn't I exchange it with 80?
Yeah, so if you exchange 68 with 80, you would then have to also exchange 80 with 91.
Yes.
So by just doing the larger one, it sort of theoretically will always be the larger of the of the new subtree. Yeah.
Good. Did people hear this? Okay, so you always exchange it with the larger one. That's what the algorithm does for the reasons you've just explained. So decrement I now, so exchange 91 with 68. Okay, so updated array is now going to be, looks like this is taking a little bit more time than okay, so that's okay. We can do graphs later. So what we'll do then is we'll do, I have some time. We'll talk about what we'll do. Okay, so we've exchanged 68 with 91. So this 91 becomes 68, and this 68 becomes 91. And my way of visualizing this tree is going to be, okay, I copied the wrong tree, but that's okay. Is going to be the following. Okay, so this is going to be from the previous, this was 97 and 1, but now I've also exchanged 91 and 68. So I have 91 here, this is 1, and this is 68. Now I've restored the heap property there at this tree. Now let's continue. Still not a heap. Step 3. So this is what you will be asked to do on the quiz. So we'll see a question like this. That's why we're going through this. Now I come down to 21. Is 21 a heap?
No.
21 is not a heap. So I equals 2. And now I'm going to update. What do I exchange 21 with?
So you exchange it with 97 because it's the greater of its two children.
Yes, that's exactly what we'll do. So let's see how this will work out. So the new tree becomes, so you just said that we need to exchange, what was it again? 97 with 21, right?
Yeah.
97 with 21. So I'm going to put 21 here, 97 here, and this is going to be 21, and 97 is going to go here. That's the updated array. Okay, step 4. Step 4. Let's use the next page. What's the step 4?
Just real quick,
Yes.
nothing actually happens with this tree, but you would also sync 21 here, right?
Why is that?
Just like evaluate and then say, okay, 21 is greater than 1, so then nothing happens.
Yes.
Okay.
The sync operation, true. Said that. So then what's the next step? I finally am down at the root. This is the last step. What's the update now? Update. Let me copy this again. How should we update these guys? Where is the heap property violated now? So I'm looking, I is 1 now. I've decremented I. Notice that I've started at length of A over 2. I started at length of A over 2, which was this node, and I came down this node, this way, and now I'm up at the root. Okay, so now 5, what's happening with 5? And I'm glad you made the point that you were making, because 5 may go down a little further in this sync operation. So 5, who do I exchange 5 with?
97.
With 97. So that's my first exchange. 5 goes here, 97 goes here. Okay, so let me update it here. 97. Then 5 goes here, right? Then I compare 5 to what? So let me put 97 is going to go here. And 5 goes here. Then what's happening?
It gets compared to 42 because that's the greater of its 2 children, and you exchange those 2.
Exactly. So now this 42 becomes a 5, and this 5 becomes a 42. So this 42 becomes a 5, and this 5 becomes a 42. And then what? Am I done?
We have the heap. We haven't
Yeah.
like output the sorted.
Yeah. Sorry, one more time.
We have the heap. I don't know if we're going to end up sorting it, but
No. It's simply, this time we're not going to ask you about sorts. So just build a heap on this quiz. So you'll see a question like this. It will tell you just please build a heap, and you'll just build a heap just like that. So what you need to do is when you see an array, you'll be given this. So what does the program itself do? The input is this array, and the output is going to be this array. So the goal there on that question will be to build a correct heap. Now this is, of course, this is the first step in heap sort. Do people remember this? This was the first step in heap sort. Now, once you have this heap, then you can sort it. Since we're at the subject, and because we'll be covering sorting later in this class, can you just remind me, since we're at this subject, how would you turn this into a sorted array now? This is not sorted yet, but you can turn this into a sorted array. What's the way to do it?
So you swap the first and the last element to start, and then sync the first element back down,
Exactly.
and then
That's
you, like,
exactly right.
yeah.
So please review that. Now this quiz, in this quiz, you're not going to have sorting questions. You will have sorting questions in the last quiz. So the quiz that's coming up, since we're done with reviewing, I think we can do the quiz on Monday. So why don't we do the quiz on Monday? Are people prepared to do this quiz on Monday? I think that would be a better thing to do. The reason for this is because, first of all, the questions have been posted there for a while, so I'm hoping that people have started at least looking at those questions. The second is that we need to do 2 more lab assignments. We need to do an assignment in graphs, that's at least 2 more, and then an assignment on sorting. Okay, so we'll do like quick sort, probably assignment. I think it's much easier for you to sort of like prepare, you just have this like quiz questions prepared and done by Monday for sure, thoroughly, so that you can ace the quiz. And then I'll post the graph assignments. We haven't even started talking about graphs, but I'll post the graph assignment now, like tomorrow morning, and that will be due, I guess, on Wednesday, right? And then I'll post another assignment on sorting. So we actually have quite some stuff to do. So that said, let me now switch. Any questions about these questions? Okay, how about the linear probing questions? Are those clear? Is it clear what linear probing does? It's in the, so did you guys read the reading assignment or watch the videos, whatever? Andrew has videos on this. I'm sure I haven't watched them, but I know he has videos and people watching those. Or maybe you have favorites on but the reading assignment. So is it clear what linear probing does? Okay, so please bring those questions then next time, like before the quiz, if you have that. Otherwise, we need to move on. So please review these questions that we post. Okay. Tremors. Okay, you will not be quizzed on Greek mythology, but yeah, the labyrinth you will traverse. A labyrinth. A maze, let's call it a maze. Okay, so a graph is simply a collection of entities, objects called vertices and connections between them, okay, called edges. So this is a graph. Those dots there are vertices, and the edges are shown as arrows here. The edges can be directed or undirected. If the edges are directed, they're shown as arrows in a visual representation of a graph. That's just an aid for us. This object is what we call a graph. Inside a computer, it's represented in a slightly different way, and we'll talk about that in a minute. The edges can be undirected as well. Okay, so if the edges are undirected, they usually represent a symmetric relation between the objects, the entities, the vertices that it connects. For example, you could draw a friendship graph, or let's take this class. So we have about 40 people in the two sections. If two people have collaborated on a homework, we'll draw an edge between them. If they've never collaborated on a homework, we don't draw an edge. You'll end up with an undirected graph like this. Okay, two distinct vertices will be connected if those two people collaborated, and will not be connected if they did not collaborate. Okay, you will obviously not have any self loops. Okay, we don't draw them. There's okay, loops around the vertices, and they are undirected because the relationship is symmetric. You cannot have one person collaborate with the other and the other person not collaborate with the first. Another thing, okay, so where would a directed graph be used? Okay, so if you draw, for example, a graph of people, so people are the vertices in this representation, draw an edge between two people. If one person follows the other person on Twitter, you'll draw an edge from the first person to the second. Okay, if the second person does not follow the first on Twitter, then the edge will be unidirectional from the first to the second. Okay, so in this context, it makes sense to have one directional edges. And there are plenty of applications. Now, the vertices here represent states in the United States, and the edges are drawn between two vertices if those states border one another. For example, there is no edge between Vermont and Delaware because those two states do not share a border. Okay, here, Vermont is drawn here. Here's a node that represents Delaware. Okay, but Maryland and Delaware are connected because they share a border, and so on. So you get the idea. Here's another example of the friendship graph on Facebook. Okay, there are lines. Lines represent people connected on Facebook somehow, and so on and so forth. There are plenty of applications of graphs. For example, let's take one or two of these rows. Transportation network. Okay, a vertex is an intersection of two streets. Okay, connection between two vertices is the road between the two intersections, like in Philadelphia, for example. 12th and Montgomery, and I don't know, 11th and Montgomery. Those two are intersections, and the road, Montgomery from 12th to 11th, that's an edge. You can draw a graph representing that network. Okay, and okay, you see other examples here. Okay, so a molecule, for example, in chemistry. The atoms can represent the vertices, and those atoms that bond, there are edges between them. Okay, so on and so forth. Okay, so there's this terminology that we'll use, edge and vertex. I think that's clear. The degree of a vertex is the number of vertices that it is connected to by an edge. Okay, it's also called neighbors. So for example, the degree of this vertex here that I'm pointing to is 3 because you have 3 edges emanating from it. Okay. Okay, so there are many problems that we want to solve using graphs. One of those problems is the so-called ST path. Okay, so you have a start vertex marked by S, and you have a T vertex marked by called a terminal vertex. You want to find the shortest path from the start vertex to the terminal vertex. There are other problems that we'll talk about them as we go along, maybe, but I don't want to spend time right now discussing them. Maybe next time. Okay, so all these problems show up in applications. Some of these are very, very difficult problems. Others are very straightforward. By difficulty, I mean the time complexity to solve it is exponential. Others are straightforward. And that's something that we probably won't get a chance to talk about by the end of the class. But I was planning to talk about something called NP completeness, but it doesn't seem like we'll end up doing it. Okay, so, okay, now how do we represent graphs in this class? Most important piece. Okay, so here's a graph. Here's an example graph. So this graph here, it has 3 connected components here. This is one connected component. This is another connected component, and that's another connected component. Okay, there is no way to reach a vertex in one connected component from a vertex in another connected component, right? There's simply no path between those 2 vertices. Now, these 2 graphs actually are the same graph. The way we draw the graph is completely irrelevant. Inside the computer, they're represented identically. The way we position those vertices on the plane, not important at all. Okay, so these are the same graph. There's a notion of graph isomorphism, which we're not going to touch, but these are identical graphs here. Okay, let's see. We'll use integers in this class to represent the nodes, just to simplify life. Obviously, you can build the association. You can have nodes of strings. That's not too difficult to change. Or you can store other kinds of data at the nodes. But we'll store either characters, or I think we'll store integers would be the simplest, or characters, wouldn't matter. But these are the graphs. Okay, so this is the graph that we'll deal with, for example. So here's our graph API. We're going to have 2 constructors in our graphs. We will have a way of creating a graph with a certain number of vertices with no edges between them. We'll call that an empty graph that has no edges. And we'll have a special constructor for it. We'll run code and see how it works exactly, if not today, then on Monday. We'll also want to read large graphs from the files or from somewhere on the internet, stored in text files. So we'll store these graphs in some way. We'll talk about ways of storing those graphs in text files as well. It's pretty straightforward. So you want to be able to read this file, the text file, and build a graph using that input. So you also want this ability to add an edge, pass vertices to this method, add edge, and build an edge to update the graph accordingly. So if the graph didn't have an edge between vertices 7 and 25,000, then add edge 7, 25,000 will add an edge between those 2 vertices. This one gives you what's called the adjacency list of a vertex. An adjacency list of a vertex is the list of all vertices to which it is connected. So for example, going back a little bit like this, what's the adjacency list of A? Well, A is connected to F, B, C, and G. So with A, we'll associate an array, which will be an array list in our case. And that array list will contain all these vertices in it, all these vertices. Like A's adjacency list will contain F, B, C, and G in some order. The order of those does not matter. Okay, and then we'll also have convenience methods called V and E. This one returns the number of vertices in the graph, and this one returns the number of edges in the graph. That's it. That's our graph API. Now, unfortunately, we're running out of time at the wrong place because we really wanted to run this and look at the maze and all of it. But if you go now to Canvas, and if you click on this graph starter code, so apparently this is not going to happen today. It's going to happen when? On November 16. So this will be the starter code for November 16. Okay. If you click on this maze and draw, if you download, please download those before Monday, because we want to not only do the quiz on Monday, but we also want to talk about graphs going, because we have stuff to cover about graphs. Quite a few things. We want to talk about depth first search, breadth first search, and Dijkstra's algorithm. So these 3 topics we must finish on Wednesday. So there's quite a few things to do. So please make sure you look at the slides before next time. You can download this maze and draw. Okay, if you download all of these into the same project, you can just click on maze and see what it does. Okay. Okay, now I'm not going to run it now, but some of you have run this, and those of you who have run this, does that work on your side?
Yeah, it brings up the animation.
Okay, So the animation, the way of building that graph and putting it on the screen and so on, that's not that important for us. What's important for us is to read the graphs and have you run the graph itself. If you click on the graph, that should also run, right? And it's a good idea to take a look at the way that's constructed, right? And look over the slides before next time. Because next time we have to talk about a couple of algorithms on graphs.
The graph works too.
Okay, good. Okay. All right. Any questions about what we've covered today? Okay. So again, two major topics. Graphs, it's a major topic now. And then I guess when we return from the break, we have to wrap up with sorting. We have a couple of sorting algorithms to discuss, especially merge sort and quick sort, two algorithms. And one simple algorithm like insertion sort.